Humankind, residents of Earth, nestled within the solar system, Orion Arm, Milky Way galaxy, local group and Virgo supercluster. In the vastness of space, time is but a fleeting moment. With 4 billion years past, at the moment of the sun fading away, what legacy will we leave behind? Voyager, the greatest adventure, it has now been traveling through space for 46 years, embarking on a one-minute journey that has taken it 24.3 billion kilometers away from Earth. Every second, it ventures into a region where we have never been before. This mission was designed to meticulously study the outer planets of our solar system and to collect data and images of Jupiter, Saturn, Uranus, and Neptune. Ultimately, after completing its primary objective, Voyager entered interstellar space to provide us with a better understanding of the interstellar medium and its effects on our solar system. Additionally, it offers humanity a chance to communicate with extraterrestrial beings, serving as a messenger carrying messages from people of Earth to anyone who might encounter. It's the most audacious mission in the history. Who would have thought that we'd be able to do that in 1977? As Carl Sagan, one of the scientists behind the Voyager mission said, "Dreams are maps. Without them, we go nowhere." Back then, before Voyager, our understanding of distant planet was very limited. We only had basic information from telescopes and alien missions. So NASA decided to plan a project to explore the outer planet, Jupiter, Saturn, Uranus, and Neptune. The goal was to study their atmosphere, magnetic field, geological feature, and moons. In those days, scientists referred to the mission as the Outer Planet Ground Tour, the project with an estimated cost exceeding $1 billion. The key factor were time and equipment. Regarding time, they understood that an opportunity exists that could put us 20 years ahead. This phenomenon, which occurs every 176 years, last happened during Thomas Jefferson's presidency. It was the crucial element that made this mission possible: gravity assist. They leveraged this phenomenon to use the gravity of each planet to gain a bit more speed. In 1977, the planet aligned in such a way that the spacecraft could use the gravity of all the planets like a slingshot. To achieve its goal of exploring the outer planet, NASA planned the construction of the Voyager spacecraft. The Voyager team was innovative and understood that once the spacecraft were launched, it couldn't be brought back for repairs. Therefore, they had to design Voyager with the technology of that time so that it could operate for many years. The Voyager spacecraft consists of 6 essential parts, utilizing the technology available at the time. The Common Computer Subsystem (CCS) handles the sequencing and control functions. It contains routines for common decoding, fault detection, and correction. Antenna pointing and spacecraft sequencing. This subsystem is a crucial component of the bus housing electronics. Stability, control, and orientation. The Voyager spacecraft utilizes the Attitude and Attribution Control Subsystem, ACS, as part of its housing electronics. The subsystem is responsible for 3-axis stabilization and orientation control. It uses celestial or gyro reference attitude control to ensure the high-gain antenna remain point toward Earth, manage spacecraft orientation, control attitude, maneuvers, and position the scan platform. Communication with Earth is managed through the high-gain antenna, which plays a critical role in maintaining contact with the spacecraft. It utilizes a span for oblique command at 60 bits per second and an X-band transmitter for downlink telemetry and 160 bits per second or 104 kilobits per second for high-rate plasma wave data playback. The optical calibration target aids in calibrating optical instrument, thereby indirectly supporting communication accuracy. Data is transmitted and received through the 3 and 7 meter high-gain antenna, ensuring a reliable link between the spacecraft and Earth. Power supply. The spacecraft are powered by 3 radioisotope thermoelectric generators, RTGS, currently providing about 249 watt each. As power decreases over time, some systems must be turned off to prevent demand from exceeding supply, which reduces some spacecraft capabilities. After Voyager 1 and 2 were created, the team realized that the path the spacecraft took could have another purpose beyond their primary mission. Over 2,600 years ago, the Assyrian king Esarhaddon declared, "I made steels of stone, clay tablet inscribed with my deeds, and set up for future days." In 1970, NASA's Voyager mission were poised to become the furthest reaching object ever made by humans. The Voyager team, led by the visionary Carl Sagan, saw an extraordinary opportunity. What if this spacecraft journeying far beyond our solar system encountered extraterrestrial life? How could we communicate with them? The answer was the golden record. Carl Sagan was tasked with an extraordinary challenge: to represent the essence of Earth on a single record, and he had only 6 weeks to accomplish it. The golden record was needed to encapsulate our planet's culture, music, and language. The golden record's creation was a multi-step process with many contributors. Blank records from Pyrolis A in France were sent to the JVC Cutting Center in Colorado to cut the lacquer masters. These masters were then sent to the James G. Lee Record Processing Center in California, where 8 Voyager records were gold-plated on August 23, 1977. The 12-inch gold-plated copper records were placed in aluminum container and delivered to JPL. The cover also featured an ultra-pure sample of uranium-238. It was designed to protect the record from physical damage and space radiation, ensuring its longevity in the harsh environment of space, which has a half-life of 4,468 billion years. Each golden record had the inscription, "To the maker of the music, all world, all time." Linda Salzman, an American artist and writer, helped design the cover. The cover includes diagram and instrument to help any extraterrestrial being understand how to play the record and decode its content. The record itself was designed to be easily understood, featuring several key components. In the top left corner, a drawing of the photograph, record, and stylus in the correct position to play from the beginning. Binary arithmetic indicate the time of the rotation based on the hydrogen atom's transition period. Below this, a side view shows the time to play one side, about an hour. On the top right corner, show how to create picture from the recorded signals. It included the signal that start picture, the time for each picture line, and a sample picture for verification. On the lower left corner displays a map of the solar system's location using 14 pulsars. The unique rotation rate of these pulsars help pinpoint Earth's position in the Milky Way, acting as a cosmic address for extraterrestrial civilization. Lower right corner illustrate a hydrogen atom in its two lowest states, providing a basic timescale to help interpret the information on the cover and the decoded pictures. Imagine being Carl Sagan, tasked with introducing Earth to an advanced spacefaring civilization. This was the challenge when creating the Voyager Golden Record. Sagan wrote, "The spacecraft will be encountered and the record play only if there are advanced spacefaring civilization in interstellar space. They include a 90-minute selection of music from various cultures and eras, spoken greeting in 55 languages. The audio content include natural sound like volcano, earthquake, thunder, animal sound like crickets, frog and wild dogs, human sound like footstep, heartbeat, laughter and kiss, industrial sound like tractor, Morse code, and various transportation noises." In a touching story, Carl Sagan's sons suggest the message, "Greeting to you, whoever you are. We come in friendship to those who are friends." The Voyager Golden Record is more than just a message in a bottle. It is our legacy that remains. After 5 years of careful planning and assembling 6,500 spacecraft parts, journalists gathered at Cape Canaveral, Florida in summer of 1977 for the Voyager launches. Voyager 2 launched first, followed by Voyager 1, which overtook it by December. During the initial launch, NASA lost contact with the spacecraft for several days. Voyager 2 also faced a full leak at ignition. Despite this issue, both Voyagers successfully launched, making a triumph of human ingenuity and perseverance and the start of the journey to expand our understanding of the cosmos. In March 1979, Voyager 1 reached Jupiter and sent back the first close-up image of this planet. These photos arriving every 48 seconds show detail of Jupiter Great Red Spot, a massive storm 3 times the size of Earth, active since at least 1644. Voyager 1 relieved Jupiter complex structure made of helium and hydrogen, and its intense radiation of magnetic fields. Thanks to its aluminium shielding, the spacecraft remained safe. The mission also discovered active volcano on Jupiter's moon Io and a frozen ocean on Europe, with twice the water of Earth's surface. Using Jupiter's gravity, Voyager 1 speed up to 36,000 miles per hour, heading to Saturn next. Voyager 1 journey reminds us how vast space is. Even at 10 miles per second, it would take 10 years to leave our solar system. The nearest galaxy, Andromeda, is 2 million light years away, and we won't collide with it for about 5 billion years. In 1980, we experienced our first encounter with Saturn, unveiling its majestic ring. Its atmosphere, dense and mysterious, captivated our imagination. But the true marvel was Titan, Saturn's largest moon. With an atmosphere 4 times denser than Earth's, Titan hinted at hydrocarbon seas, beckoning scientists to delve deeper. Scientists made the bold decision to redirect Voyager 1 toward Titan for a further explanation. After navigating through its thick atmosphere, Voyager emerged triumphant, capturing invaluable data before embarking on its continued journey through the cosmos. Meanwhile, Voyager 2 set its sights on Neptune, venturing toward the outer reaches of our solar system. It too would capture breathtaking images, offering a glimpse into the intricate detail of Jupiter's ring up close. In January 1986, Voyager 2 approached Uranus, a distant giant in our solar system with a methane-rich atmosphere. As the spacecraft neared, it made surprising discoveries. Uranus has a ring, a unique magnetic field, and a gravitational pull. Its tidal axis causes it to roll on its side, leading to an unusual orbit. Voyager 2 had a negative carefully around Uranus' orbit to continue its journey to Neptune. During its exploration, Voyager 2 discovered 2 new rings around Uranus and provided valuable data on the planet's composition and structure. It also observed Miranda, one of the Uranus moons, which approached heavily fractured, hinting at the tumultuous past. This 10-month Voyager brought Voyager 2 closer to its new destination, Neptune. It took another 3.5 years for Voyager 2 to reach its final planetary target, Neptune, marking its 10th anniversary of its launch. By then, Voyager had traveled about 30 times the distance between the Earth and the Sun. As it ventured further into space, it faced new challenges, such as operating with less sunlight and in colder temperatures, pushing its engineering to the limits. Despite these obstacles, it continued to capture groundbreaking images. In 1989, Voyager 2 reached Neptune, providing humanity with its first close-up image of the distant icy giant. These images relieved Neptune's great dark spot, a massive storm similar to Jupiter's great red spot, and 2 of its faint rings. Additionally, Voyager 2 discovered Neptune's largest moon, Triton, covered in frozen nitrogen. Triton showcased active geysers, with plumes of nitrogen gas and dust exceeding kilometers into space. Voyager had reached the end of its primary mission, marking a monumental achievement for NASA and all of humanity. At the incredible distance where Voyager was located, the light was so faint that capturing photographs was an enormous challenge. Yet, this didn't deter Carl Sagan from pushing NASA to attempt a photograph of Earth. From nearly 4 billion miles away, Voyager 1's camera was pointed back toward its birthplace to capture one of the most iconic images in human history. On Valentine's Day 1990, Voyager 1 took a photograph of Earth, which approached as a tiny speck suspended in sunbeam, famously known as pale blue dot. As Carl Sagan eloquently put it, "This is where we live, on that blue dot. On that blue dot is everyone you ever known, everyone you have ever heard of, every human being whoever was, live out their lives." we still maintain communication with Voyager 1 and Voyager 2 using a network of antennas located in California, Madrid, and Canberra, Australia. It takes about 22.5 hours to message to reach Voyager 1 and nearly 19 hours for Voyager 2. This station received their faint signals, now less than 1 trillion of watts. Currently, Voyager faces challenges such as freezing temperatures and limited power. Various components are shutting down, increasing the risk of a spacecraft freezing. Communication is often difficult due to Voyager's position relative to Earth, especially when it's below the horizon, and only the station in Australia can receive signals. As time progresses and Voyager's full depletes, final expected shutdown of the science instrument is anticipated around 2025. Engineering data might still be transmitted until approximately 2036, when the spacecraft is expected to drift out of range of Deep Space Network (DNS). The Voyager project, once supported by 1,200 people, is now managed by a dedicated team of just 10. When the spacecraft run out of fuel in the coming years, the team will bring the mission to its conclusion. Today, the Voyager have ventured into interstellar space, carrying the golden record, which might be discovered someday. The sun's magnetic field extends far beyond the planet, creating the heliosphere around our solar system. It wasn't clear how long it would take for Voyager to exit this bubble. Since Voyager 2 flyby of Neptune in 1989, the team eagerly awaited this milestone. In 2012, Voyager 1 crossed into interstellar space, becoming the first human-made object to do so. After the Voyager power depletes, their mission continued with the golden record, designed to last 1 billion years, potentially preserving the story of humanity long after we're gone. The protective cover ensured it remain intact in a quiet, hazard-free environment of interstellar space. In 4 billion years, when our sun transformed into a red giant, Voyager will still be traveling through interstellar space, carrying the story of our world into the cosmos.